Okay, Year 12. This is the second section of Chapter 4, Electrical Circuits, and again, it's one of the crucial ones, but it's there in the background. So I'm only going to talk through the first part of Section 1. It's mainly going to be about doing the experiments themselves, looking for patterns, etc. Okay, so before we actually get into using electrical circuits and working out how they all go together, we need those two parts. So firstly, we need to really make sure that we have, if I pick up from the first section, a really good idea of the key things that we can measure in a circuit. So that's going to be the current, flowing, taking energy, etc. How much energy they've been given, so the voltage that is known as EMF, how much energy they give out, so that's the other voltage, PD. And how does that link together? Well, it's all to do with how much opposition there is to that current flowing. Okay, so these are the cornerstones of electrical circuits. Delivering electrical energy depends on knowing how those three key ideas link together: energy, flow that transfers that energy, and what it is that causes that energy to be left at some place, okay, which is resistance. So the key components link them all together, but actually it's this bit down here that often is the cause of stuff that we're interested in, okay, and it's one of those things that comes first. So let's look at the cornerstone of electricity, which is Ohm's law. Okay, electrical characteristics means really about how much something in a circuit will take from a circuit, so how much energy, PD, how it depends on how quickly it's being delivered, current, and that's going to depend on the device that it's flowing through. So we really need some background idea of what is causing energy to be taken from the current by different devices. Okay, and the name that's most associated with this is, of course, Georges-Simon Ohm, who came up with the original definition for which led us into resistance. Okay, what he actually said was, for IV characteristics, okay, current voltage characteristics, he said the current flowing into a device, okay, or through a device, is proportional to the PD. Again, we're going to use that for short, so the type of voltage, the PD, applied to the component. Now it can be said in reverse that, so you could say the PD at a device, at a component, depends on the current flowing through it. It's an either or, so it kind of works both ways. For me, I tend to work on the voltage from it. However, and this is the crucial bit, this only works if. Okay, so there are some caveats, or one caveat that goes into this that really, really matters. So as long as external factors, things that affect it, are constant. Now, most people, if you learn that at GCSE, we're really thinking about temperature. That's a pretty obvious external factor, but there are others, okay, and there are other crucial ways around it. So this is the cornerstone of everything. Everything obeys Ohm's law as long as you're not changing these other factors. And as soon as these other factors are changed by external inputs or what you do to a circuit, then this all changes. But this is our cornerstone. So Ohm's law is not the equation, okay, it links into the equation. It's really what he's saying is, on his graph the gradient has a constant value, and that is what we call now resistance measured in ohms. But that came afterwards, that came from him. So it is this that he discovered, the law itself. Voltage is proportional to current. So if we want to find out about components, we need to plug them into a circuit that is measurable. and the only things you really can measure are these two things here. You have voltmeters, you have ammeters. You can't really measure much else with certainty. Everything else that comes into these other fancy meters actually still measure these and use those to calculate something for your behalf. Okay, so it's all about current, it's all about voltage. The voltage given out by something, so PD and current. So how do we actually test things? Well, we just simply measure the voltage and the current through them. Okay, so to do that we have a classic resistance circuit, and it's the basis of all circuits. They're all based around this principle. So if you want to take measurements, if you want to see how things vary, then we need to use certain key components. We need to be able to plot it over time, okay, and over the changing conditions. So this leads to the idea of a graph. So we need an energy source, and that is going to be our EMF, so I'm going to give it the curly E. Okay, so the voltage provided to the circuit, energy given to each charge. And then what we're going to do is we're going to run that through an adjuster. So we have something called a potentiometer, okay, or given a different name sometimes, which depends on how you use it, but potentiometer is basically a resistance wire, and if we connect that in a circuit, then depending where you connect on it, you can vary your values. You can supply more or less energy to it. So you can divert energy to the circuit, or we can get the current flowing back, collecting more energy. Now, this does drain. Okay, so this very importantly always comes with a switch. Okay, so we basically have a large resistance. Okay, so as I say there, a potentiometer, because it's the potential changes with the length, so it's kind of like a dial in a way, but sometimes it's called a pot or potential divider. Okay, and we'll look at that in more detail. So we will supply electricity, could be connected to the top, could be connected to the bottom. Conveniently we tend to do it off this bottom. We tend to assume that this is 0 volts. It isn't necessarily, but it tend to assume. And then that goes to our circuit, our component that we're going to test. Now we want to know what flows through it, so we are going to have an ammeter, and usually, not always, but usually that comes before the thing that we're testing. So we want to see what flows in and of course flows out. We want to see what's left behind at this point as well, so whatever we connect in here. So I'm just going to turn this around sideways, and I'm going to write in to the component. I don't know, can't spell it like that. Component. Okay, so to whatever you're testing. It could be a circuit that you're testing. It could be one thing. But that's connected into that space there. And what you want to do is you want to see how much energy is left there. So you will find out what you had before, what you have afterwards, and you're going to find the difference between them, the difference in the potential energy that it has. So we have a potential difference meter or voltmeter. Okay, so it measures in volts, hence we call it a voltmeter, but it actually is measuring potential difference. Difference before, difference afterwards, connected across the thing that you are testing. How much flows into it, etc., will adjust how much is left there. So this will depend on this. You need to know what's going in. I should say you could have it afterwards. Doesn't matter, as long as you've got the current flowing through the thing that you're testing. Now, symbols wise, this is an adjuster, so we have an arrow connected to it, and literally we will use a machine called a rheostat for you to do this. So it is a high current device that has a certain name, but it's used as a potentiometer. You will slide the contact up and down, and what that means is you can adjust the energy given to it. It's a bit like a ladder in that when it's right down here, the difference between the top and bottom is nothing. There's no difference here. If we connect it, slide it up to the top, then we will get the full voltage, the full EMF dropped across here, so we get full voltage. Anywhere in between, it adjusts. So halfway down, you'll get half the voltage. So those are our key principles. The rest is then how things behave. So what we've got is something that only obeys Ohm's law, is truly ohmic, as it's called. I'll leave you to think about that. But we will often not just look at the potential and the current. Things behave, components behave differently on how they're connected. So things that are not passive, things that you don't just let the current flow through and see what happens, but things that can change and control electricity, they can be designed to work in different directions. So we will always measure what happens to the current when we reverse the direction. So we'll put a minus current and a minus PD. So we're looking at results here when we've got your voltage and current connected, and then we'll swap the direction, we'll swap the connectors here, or move your component so it's the other way around. Doesn't matter which, the event is the same, and you'll end up with current and voltage in the opposite direction, so you'll end up with negative. So nothing's ever up in this top left, bottom right corner. We've always got something here and here. So we've got an ohmic conductor, okay, or resistor, same thing. A good resistor is a bad conductor, but they are both conducting, both resisting. So an ohmic conductor or ohmic resistor, we're going to look at things that get hot. Most things will get hot to some extent, but again, filament lamp is designed to get hot, so it will glow. So we'll look at that as well. And then we'll look at things that aren't just made of metal, so not just metallic bonding, where we start looking at more cleverly designed stuff. So we can have a passive device again that works on semiconductors rather than metals. So that's a thermistor, and that's fairly typical. You can get two types, but the ones that are the simplest, the ones that work just on being a semiconductor, are usually negative temperature coefficient. So I've put it here for you. The resistance will go down as the temperature goes up, but I'm going to get you to find out the voltage current characteristics because that's important. LDRs, light dependent resistors, again it's a semiconductor, fairly passive, slightly more advanced in terms of its construction. And then the first and simplest of the active devices that are actually designed to change when they do things, but leading us all into all the semiconductor world, so transistors and everything that is based upon transistors. There are two main types of transistors, there's actually three. Some are high power devices designed to control power, some are just designed to switches, turning on and off. Digital computers are just switches. So there are different components, but again, diodes are actually made of several materials, or rather semiconductor active devices made of several materials. A diode only two materials, but again they behave together in a certain way. So that's your main bit that comes from this. We're going to look at how we use the meters in different ways, but the key points are, oops, wrong sheet. The key points are that we're really trying to find out how materials behave by looking at how much energy is deposited by each charge as it flows in through your ammeter. And this is our adjustable circuit that makes it happen. So there's our basically variable power pack. That's our measuring part of the system.